All right. Next chapter, gases. Now, hey, this is the last section.
Huh?
Yeah, this stuff starts the last exam
Oh.
for the entire class, this whole semester.
So.
Okay. All right. So we're going to learn about gases. We're going to talk about the ideal gas, okay, and its equation. Then we're going to get to how we apply that. Then we're going to get to real gases, okay? And so the ideal gas is ideally how it should behave all the time. And then we'll tell you what really happens, okay? And there are some things in which we have to account for a real gas, okay? And so gases, unit 10. Now, really, what is the difference between a solid, liquid, and gas? Okay. All right, here is what a solid looks like. If I look at it, molecule, next to a molecule, next to a molecule, next to a molecule, and they're next to each other, okay? And so one thing about it, though, is they are vibrating. Why are they vibrating? Why are the atoms actually vibrating? Energy. What kind of energy? Potential energy? No, not because they're vibrating. It's the other type, kinetic. And kinetic energy, the energy of movement, comes from what thing that we can measure? What is something we can measure that measures kinetic energy? Not electronegativity. It's temperature. Everything that has temperature, the molecules are vibrating just a little bit. But the solids, the molecules do not have enough energy to move past each other. They're vibrating, but they're stationary. Okay? They move a little bit, but they can't go past each other. The attraction between the molecules is so much that even though they're vibrating and even though they have energy, they're stuck. That's why a solid retains its shape. Okay? Now, the liquid, on the other hand, they're still touching. But they're not just vibrating. Okay? They're actually moving. All right? And they have enough energy to move past each other, but they can't separate. They're always touching another molecule, but they move past each other. And so if you place them in a container, they will move to the edges and take up the shape of the container. Okay. Here's a gas. Okay. They behave differently. The gases are moving so fast that they are not touching each other. Okay? They are moving so fast that they really don't interact with each other. And they will take the shape of the container because they're moving in straight lines, and they'll go until they hit something and then bounce back, and go until they hit something and bounce back. And so a gas will take the shape of its container, but the molecules are moving much, much faster. All right, how do we change something from a solid to a gas? If I had a piece of ice, how do I make that gas? You heat it. You add more kinetic energy until the molecules will slide past each other rather than being in the ice. And then once they slide past each other, we can get them moving so fast that they will jump out away from each other and create steam. Each one, the solid has certain characteristics, the liquid has certain characteristics, and the gas has certain characteristics. I can compress gases because there's space between the molecules. And I can expand it, and I can compress it. But I cannot compress liquids or solids because the molecules are already touching each other. There's no place to push down anymore. And so the molecules of the gas behave differently than that of the solids and liquids, and it is because they have so much energy, okay, that they are very far apart from each other. They behave like they're all by themselves, and they take up a very small fraction of the space that they're in. Okay? So most gases are really, in true life, small molecular compounds. They're usually nonmetals. They expand to fill containers. They can be compressed, and the movement of the molecules are very fast. We'll actually determine how fast they actually move. Each molecule behaves like it's all by itself, so every individual molecule is not influenced by the other molecules in the sample. And because gases are so far apart, the volume only represents a very small fraction, less than 0.1% of the total volume, and this is important for how they behave. Vapors is a term for a gas, but a vapor is a compound that is normally a liquid and solid at that particular temperature. So the water in the air is called a vapor. We also call it humidity. Right now, it is not 100 degrees Celsius and water doesn't boil, but some water evaporates, and that's called a vapor. There's one gas that you interact with every day, and that is air. It is a homogeneous mixture of the two gases, nitrogen and oxygen, which make up 99% of all of the gas. The last percent is made up of all the other gases that you see on the chart, plus a little bit of methane, a little bit of carbon dioxide, a little bit of carbon monoxide, all the gases that exist. The three most easily characterized measurements of a gas, and we're chemists, so we like to measure things, are temperature, volume, and pressure. How do you measure a temperature of gas? Thermometer. How do I measure the temperature of the gas in this room? I put the thermometer in the gas, put it out there, and I measure the temperature. So you just put it inside the gas. That's easy to measure. Volume. How do I measure the volume of a gas? You put the gas in a container. You know the container's volume. Okay? And so that defines what the volume is. Okay? And the pressure, we will use a pressure gauge of some sort to measure those. So those are three things that we can measure very easily about a gas. And so we take lots and lots of measurements about temperature, volume, and pressure. Now pressure we need to define a little bit. Okay? Pressure is a force acted upon by an area. Okay? And so the pressure that we talk about most often and we reference is air pressure, the pressure of air. Okay? And what we do is we know that there's air in the atmosphere, and we know that the gravity of Earth is holding that air to us, okay, to the Earth. And so what we need to do and what we've done is we've measured how much force is the air pushing on us. Now, essentially this. What we measure is the air from the top of your head to the edge of space, okay? All of that air is being pushed down on top of your head, okay? And so there's a pressure that's being pushed, and it's actually pushing all around us onto us. And we're going to measure that amount. Now, I don't feel it because the pressure inside of me is pushing out. The pressure is being pushed in, and we're at equilibrium. Is there ever a time in which you are not at equilibrium and you feel it? Have you ever gone in an airplane? What happens to your ears? They pop. What happens is you go up above the atmosphere or higher into the atmosphere. There's less air pushing down on you. There's less air pushing down on you. There's less pressure. But inside your ear, there's pressure pushing out. You feel the discomfort because there's an imbalance. You're not equalized. But when you pop your ears, you equalize and you don't feel it anymore. Yes?
What about when you're in water?
When you're in water, the air is pushing down on you, and then the water pressure pushes down on you. And so you feel more pressure underwater. You feel both the water's pressure and the air's pressure. So if I take a look at this force times an area, well, let's choose an area, okay, and choose a force. Well, a force is mass of the air times the gravity or acceleration, and we know the gravity of the Earth, and we have to estimate the mass. The force is called Newton. It has a unit of gram times a meter divided by a second squared. Okay. So 10,000 kilograms is approximately the amount of air that is in 1 square meter from the Earth's surface to the edge of space. Okay, do you know what a kilogram is in pounds? It's about 2.2-ish. Gotcha. All right, so 2.2 times 10,000 is 22,000 pounds, divided by 2,000 is 11 tons. 11 tons of air are being pulled down by gravity in that meter area, okay? A meter squared. That's a crazy amount of air, but it doesn't crush us because we have pressure equalized. When we get all this done, it comes approximately to 1 times 10 to the 5th newtons, okay? And if I divide that by a meter squared, then I get a new unit, okay? A newton divided by a meter squared is called a Pascal. That is a unit of pressure, and it's approximately 1 times 10 to the 2 kilopascals, or about 100 kilopascals, okay? Now, that is not an absolute accurate measurement. It is an estimate. About 100 kilopascals is the unit of scientific pressures. Remember, there are only 7 units in the scientific measurement system, and then we make lots of derived units. And so volume was a derived unit. A liter is derived from some of the basics. The Pascal is the derived unit for pressure. Okay. In real life, okay, the actual measurement in kilopascals is 101.325. Kilopascals makes 1 normal pressure. We also use, and this is most often, we round that to this, 1 atmosphere. That one's easy to remember. The normal air pressure of anything is 1 atmosphere. We use that quite often, right? Even though kilopascal is the definitional unit, ATM you're going to use much, much more often. But we also measure in millimeters of mercury, or torr. 760 millimeters of mercury. Okay, what's happening here? An old barometer does this. Here is the air pressure pushing down. Okay? Then I have this tube that is closed at the top. That's important. It's closed at the top. And there's mercury inside. The amount of air pressing down and the amount of pressure of the mercury inside the tube will become equal. At normal pressures, the height of this is 760 millimeters of mercury height. This is how we use an old barometer that has mercury in it. We used to have one that was open to the air. We don't use that anymore because mercury is dangerous. Okay? But it would take 760 millimeters of mercury inside that tube to equal all of the weight of the air pushing down on that same pool of mercury. All right? And so that is a measurement that we can use. A guy named Torsolini did a whole bunch of work with pressures, and so instead of using millimeters of mercury, we've used and changed that unit to a torr, and that's why you get 760 torr is the same as 700 millimeters of mercury, or 760 millimeters of mercury. If by chance you instead used water, water is not as dense. It would take about 10 feet of water in a tube to equal the air pressure. 10 feet is kind of hard to measure. To actually see the top of and measure it, we don't use water. It's too light. It's not dense enough. We use mercury. Now we do a whole lot of measurements that simulate mercury. We don't use mercury too often. Okay, here's the unfortunate thing. Units for pressure can be a lot. We can go millimeters to atmospheres. We can go torr to atmospheres. Okay, millimeters to atmospheres, torrs to atmosphere. 1 millimeter is 1 torr. We can go kilopascals to atmospheres. We can go pascals to atmospheres. We can also do this, 14.7 PSI. Do you know what PSI stands for? Pressure per square inch. It's actually pounds per square inch, actually. In that, the pressure, normal atmosphere, 1 square inch on your forehead, there's 14.7 pounds pressing on it because of the air pressure right on that square inch. Okay. Now, look at all of those different measurements of pressures. What are they all being equated to? What is the most often pressure unit on that whole chart? Atmospheres. Whatever you're given, almost always you're going to be changing it to atmospheres to actually use the pressure. Now, here's the deal. If you have to use pressures, why don't we give you pressures all the time? It's CHEM-111. Okay? And so you won't be given pressures all the time. And so, but you can convert these. If I want to go ATMs to torr, okay, it's just a conversion factor. 1 atmosphere is 760 torr, and you can calculate the torr. If you want to change torr to atmosphere, this is the same conversion factor. I just use it in a different way. Or kilopascals to torr, okay. You don't have, you could actually do this. 101.35 kilopascals is defined as 760 torr, or you can do 2 calculations, depending upon what you want to, or what you know. Anything that equals 1 atmosphere can be, you could simplify this calculation. You can just put 760 torr here, if you would like, and you would come up with the same mathematical calculation. So, I will give you lots and lots of different kinds of pressures. Most often you will calculate it to atmospheres. Okay. Now, what in the world do we know about gases? We actually know a lot about gases. A lot of people did experiments with gases, and what we're going to get to are what are called gas laws. Most things in chemistry and in science are theories. Okay? A few things have gotten to the stage of law. Here's what the difference between a theory and a law is. A theory, you think it's going to happen, you predict that it happens, and you test and it happens. Oh, that's good. And I test that it happens. Oh, that's good. And I test that it happens. Oh, that's good. My theory is being supported. At some point in time, there is enough experiments that go on that you are absolutely confident that this will always work out. That's when it becomes a law. Very few things have actually been determined to be a law. The gas laws are one of them. And so it's just because of thousands and thousands of experiments that they've done, they all work out right. We have laws, so we need to know these. And so there's lots of laws and lots of relationships. Okay, so first law, Boyle. Boyle is going to relate 2 things, pressure and volume. Okay, and so here's the deal. If you have a balloon and there's a gas inside that balloon, okay, if I increase the pressure, meaning that I push on every side of the balloon and I make it go smaller, inside the balloon, the pressure of the gas goes up. As I decrease the volume, the pressure goes up. Conversely, if I take the volume and I make it bigger, the pressure goes down. The relationship between these two is inverse. As one goes up, one goes down. Okay? Boyle's law. Now, mathematically, the pressure, okay, as volume equals some constant number times 1 over pressure, mathematically that works out. Now, we have to assume these 2 things. We have a constant amount, we don't change how much gas is in there, and the temperature doesn't change. As long as the temperature doesn't change, then the pressure, as it goes up, the volume goes down, or vice versa. As pressure goes up, the volume goes down. Okay, got that? Boyle's law. Chuck's law, Charles' law. He's going to relate temperature and volume. All right? And what happens with temperature and volume is that as the temperature increases, okay, the volume increases. As the temperature decreases, the volume decreases. Okay? They're directly proportional. They go in the same direction. Okay? So if I take a balloon and I heat it up, the balloon gets bigger, and I heat it up, the balloon gets bigger, and I heat it up, the balloon gets bigger, and I heat it up, the balloon gets bigger, and I heat it up, and it explodes. Okay? It isn't that the gas explodes, but my container pops. But as long as I heat it up, the gas should get bigger, bigger, and bigger, and bigger, and bigger. Okay? As I heat it up, the molecules are moving faster and faster, and they go farther. Okay? That's cool. In reverse, if I take a big volume and I cool it down, what happens to the volume? It gets what? Smaller, and I get the volume, and it gets cooler. It goes what? And if I get smaller, if I get cooler, it gets, and I cooler, 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 cooler. Eventually, theoretically, if this relationship works perfectly, there should be a temperature in which the gas volume becomes what value? Smaller, 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 0. Can the gas ever really reach 0 volume? What'll happen is the gas will start to get smaller and smaller and smaller. You can't get to a volume of 0 because the gas actually takes up physical space. But this leads to a theoretical place. Okay? Theoretically, using this gas law, there is a temperature for all gases at which the theoretical volume is 0. The numerical value of that is minus 273.15 degrees Celsius. This is termed absolute 0, the coldest anything could ever be. It is the temperature at which there is no movement, no vibration, nothing. It is a theoretical place. We have never reached absolute 0 because if we actually measure it, we put in energy and it gets warmed up. We have gotten to fractions of absolute 0, but it is the coldest anything can be. Now, if we decided where the coldest everything should be, then we start one of our temperature measurements at that place, saying 0 is absolute 0, and you go up from there. That is where the Kelvin scale starts. And 0 Kelvin is absolute 0. Okay? It is based upon this gas law. Okay? And from this point on, when we do gases, okay, the temperatures that we're going to do in calculations will be in Kelvin. Our pressures will most often be in atmospheres, and our temperatures will be in Kelvin. Very rarely will I ever give you that. Okay. There is quantity and volume. Now this one really, really goes out on a limb. And it says this one. If you have more, it takes up more space. If you have less, it takes up less space. So if you have more moles, it takes up more volume. If you have less moles, it takes up less volume. Hold up now. That one was hard. Okay. Is that indirectly or is that directly proportional? Directly proportional. All right. Avogadro got into this, and he had a hypothesis which was borne out by experimental values. Equal volumes of the gas at the same temperature and pressure will contain the same number of molecules. It doesn't matter what molecule you have at the same temperature and the same pressure at the same volume, they all have the same number of molecules. That's important. We're going to get to a constant in just a bit. Okay? Pressure and temperature. As the temperature goes up, the pressure will go up if the volume and the amount stay the same. These are directly proportional. Okay? And so mathematically, if the temperature goes up, the pressure must go up if the volume and the amount are the exact same. All right? And the other, as the amount goes up, the volume will go up. All right, here's the important part, and this is where you need to write down. This is what Avogadro said. at 0 degrees Celsius and 1 atmosphere. Okay? 1 mole of gas, which is 6.023 times 10 to the 23rd molecules of gas, will be this volume, 22.4 liters. It does not matter what gas you have. At these conditions, 0 degrees, 1 atmosphere, and 1 mole, it becomes 22.4 liters. That's kind of oddball, because gases are different sizes, okay? But it didn't matter how large each individual gas molecule was, because the size of the molecule really doesn't matter. It's the motion of the molecule, and at that temperature, that pressure, that amount, this is the volume that we have. Okay, so it will be used as a conversion factor at some point in time for you in problems. So that's important. Okay. Okay, STP. You do need to memorize this because sometimes instead of giving you in the problem actual numbers, we'll just say it's at standard temperature and pressure. So this is what we assume is standard. 0 degrees Celsius, which is 273.15 Kelvin, and 1 atmosphere. Okay? And so STP, I could say that or use those acronyms, and you now are defined what temperature and what pressure that system is at. And if you have at STP 1 mole of gas, it will be equal to 22.4 liters. This is just something that you need to know. Okay. Now we've got Boyle and Chuck and Avogadro all saying some things. Boyle said that the volume is proportional to the pressure, and that's indirectly. Charles said the volume is proportional to the temperature, that is direct. Avogadro said the volume is proportional to the amount, okay? And to make it mathematical, instead of just proportional, make it mathematical, I have to multiply it by a constant number. Some number that's constant, that's all the time, okay? If I combine all of these together, okay, I can say the volume is proportional to N, which is, you need to define this. N is number of moles, okay? T is temperature, P, and if I do this mathematically, volume equals some constant number I don't know, times some constant number I don't know, times some constant number I don't know, times NT over P, okay? Now, we determine this combination of numbers. All of these combination of constants is equal to the value called R. This is the gas constant. This is the number, and it's got a really weird unit. Okay? I know written like that, it doesn't really work out really well. Okay? But it is this, 0.8206 liters times an atmosphere, mole times a Kelvin. So when we do calculations, all volumes must be in liters so that I can cancel it out. All pressures must be in atmospheres so I can cancel that out. All amounts must be in moles, not millimoles, but moles, so it can cancel out. And all temperatures must be in Kelvin. Okay? And so I can substitute this R instead of having all that K1, K2, K3. And I get this right here, Pivner. Okay? This is the ideal gas law. Pressure times volume is equal to number of moles times the gas constant times temperature. Pivner. Almost all of your calculations will come back to this. Okay? You will be given 4 of the 5 almost all the time to do this, to do these calculations. And you find the 5th one. It is because gases behave in such regular patterns that we can make these assumptions and calculate the 5th value. So mathematically, you can memorize every one of these or memorize Pivner and know a little bit of algebra. Solve for whatever you're asked for. So when you start reading these problems, you're going to start identifying what you have. Okay? Actually, it's going to give you at least 3. Okay? Because R is a constant, you always have that. And so you start writing down what you have. You find out what you don't have, and you solve the problem for that. Okay? And so here we have calcium carbonate. Calcium carbonate, a solid, decomposes upon heating to get calcium oxide and carbon dioxide. A sample of calcium carbonate is decomposed and the carbon dioxide is collected in a 250 milliliter flask. After decomposition is complete, the gas has a pressure of 3.1 atmosphere and a temperature of 31 degrees Celsius. How many moles were generated? Okay, so in this PV equals nRT, what are we solving for? Number of what? Moles. Divide both sides by RT. I get N equals pressure over volume divided by R over T. Okay? Do I know my pressure? What is the pressure given in this problem? 1.3 atmospheres. Okay? And I multiply that by the volume. Okay? What's the volume in this? What is it? 200 and what? 50. Can I use that number? No. It's 250 mils, but I've got to change mils to liters. Okay. 1 mil is 1 e to the minus 3 divided by, all right, R. Do you know that? You may not, but you need to. Liters over atmosphere, mole over Kelvin. Times, what is your temperature? 31 degrees Celsius. What's the problem with that? Needs to be Kelvin. Okay, will give us Kelvin. All right, and so atmospheres cancel out, liters cancel out, mils cancel out. The Celsius converted into Kelvin, so Kelvin cancels out, and I get mole. Mole divided by our 1 over mole, which is on the bottom, which then becomes mole on top, mathematically. All right. If you do that calculation and set it up this way, you should get an answer of 0.013 moles of carbon dioxide. Okay? Now, here's the deal when I did this. I identified volume, wrong unit, pressure, correct unit, temperature, incorrect unit, and I identified that moles is what I'm looking for. I only had 3 given things, but I had R, which is a constant, which doesn't change, and so I could solve the problem. And so you have to identify each of the things that you're given and make sure they get to the proper unit in these calculations. Okay? I didn't solve for R. Why did I not solve for R? It's a constant. Now here's the deal. Doesn't matter what the pressure, volume, number of moles, and the temperature is, it should equal R. And so if I have a gas at one condition that has 4 different conditions, that's fine. And then if I change that gas and change something, and it changes all 4 of them, it still should equal R. So I could actually solve a problem just like this. I have the gas at one set of conditions, and the gas at the second set of conditions. They should equal each other. Okay? If I change it a little bit, these numbers do change. And so I could use this equation if by chance in the problem it gives me 1 pressure, and a second pressure, and 1 volume, and a second volume, and 1 amount of moles, and a second amount of moles, and 1 temperature. And it asks, what is the temperature of the final mixture? And so you can get problems that may make you combine 2 different conditions, but it will give you the first set of conditions and the second set of conditions. This would be a big problem. because it will have lots of unknown or lots of knowns, so you would have to be very careful as you read the problem and see, do you only have one pressure, one temperature, one thing? If you have only ones, use PV equals nRT. If you have conditions that have a first condition and a second condition, we go in a whole different direction. We will look at that the next time that we start this chapter.